Alright, so guys, in the last class we started some graph work and I explained the one that comes the first goes on the which axis. The one that comes first goes on which axis? Guys, whichever one, okay, so whichever one comes first, that goes on the which axis? Oh, by the way, y'all hearing me or nah?
Sure.
I'm hearing Shiloh. You there?
Yes, yes, sir.
Right. If I cannot quiet, I just responded to some messages. Yeah, look, Javon joining here, nice. Yeah, so whichever one, okay, whichever one is mentioned first, that's going to go on the y-axis. Whichever one is mentioned second, that's going to go on the x-axis. When you're calculating gradient, you need to take 2 points that are on your graph. 2 points on the graph. 2 points on the graph. Cool. In the last class, we would have also looked at some unit conversions, as well as the pendulum experiment. So that's what we would have looked at last class. Did we calculate? Yeah, we calculated the gradient. Just confirming, I did this with you guys or no? Wait, one moment, because this is my previous class notes as well. Guys, I did this with you all or no? Try check your notes. Did we do this or no?
Yes, sir.
Yeah, okay. And we got G to be 9.72. Just confirm that. Confirm that in your notes. Yes or no? Finally, real quiet, you know. Did we get this last class 9.72 or no?
I don't, I don't think we did the equation. You know.
Okay, well here what let me find my gradient then. It's not a problem. So in the last class, I don't think we do this graph, you know. I don't believe we did this graph. Well, let me just plot it back. It's not a problem. Okay, well let me jump straight into it. So you're saying complete the table and plot a graph of t squared versus L. So Adil, what's gonna go on the y-axis? Adil?
0.65.
Nah. So I want you to look at the title of the graph. What's the title of the graph? Which one is mentioned first?
T straight.
T squared. So whichever one is mentioned first, that's the one that's gonna go on the y-axis. So t squared is gonna go on the y-axis, and what's mentioned secondly?
L.
L. Right. So Adil, anytime you have a graph, the first one they mention that goes on the y-axis. All right.
Yes,
Let me know if you understand that.
yes, sir.
All right. Cool. So the main ones we'll be looking at is t squared, not t. Adil, not t, because we're plotting t squared versus L. So we're gonna look at t squared, and what's the other one we have to look at? What's the other part of the table we should look at?
L.
L. We should look at L. So I'm gonna label this axis t squared. I'm gonna label this one L. You'll have graph paper or no?
Uh,
Yeah or nah? Because
uh,
you're supposed to have graph paper, you know.
could find it.
Yeah, go find some graph paper. You're supposed to have graph paper. Javon, good morning. Javon, let me know if you hear me.
Yes, sir.
Alright, so Javon, in physics, do you leave your axes unlabeled? Do you label them Y, X, or do you put specific labels?
Label them.
Say that again?
Label them one.
Right, specific labels. So what was going on the y-axis? Remind me. What was going on the y-axis? T squared. And we need to put the units for that. What's the unit for t squared? Second squared, right? Because it's t squared. T represents period, and so period squared is s squared. Okay, and on the x-axis, we're gonna put L. What's the unit for L?
Meters.
While we're at it, we could put a title for the graph as well. Believe it or not, you get marks for labeling the axes and giving the graph a title. So what do you want to label this graph or title it? Javon? What do you want to name the graph? Okay, I hear Javon, but Shiloh, you want to give the graph a name?
T squared. First cell.
Alright, so we could say graph of t squared, and I can put the units t squared and s squared versus L. That's all. So when you're giving your graph a title, it's very typical. It's just like literally what they say. So graph of t squared versus L. Javon, Shiloh, I'll Adon. Are you all okay so far?
Yes, sir.
Yes, sir.
Right. When you're writing a coordinate, which one comes first, the x value or the y value? Tell me, when you're writing a coordinate, which one comes first, x or y?
Yes.
Like,
X. And in this case, which one acts like the x, t squared or L?
L.
L. So I'll put x by that, and the t squared acts as y. So what would my first coordinate be, Adil?
L. Right. That's. Oh, that will be 0.1 and 0.65.
Nah, take your time. We're not plotting t. It's t squared. Remember, it's t squared versus L. So it'll be 0.10 and
0.65 straight.
nah, again. Oh well, yeah, 0.65 squared, but that's calculated for us already, right? Because this is t squared. 0.65 squared is 0.42. Right? What about the next coordinate? What would that be?
0.2 and 0.81.
Badness. Shiloh, what's the next coordinate?
We 0.30 and 1.21.
Javon, what's the next coordinate?
0.50 and 1.99.
Aiden, I see your mic. Something wrong with your mic. Otherwise, you'll well be talking. And that's going to be 2.43. Which one do y'all want to do the scale for first? The x-axis or the y-axis? X, no problem. So let me show you an easy way to do this. What is the biggest value we have to go up to on the x-axis?
2.4.
So
Wait,
what's it?
no.
Right, so what's the biggest value we have to go up to on the x-axis here? Look at the x values. What's the biggest value?
0.6.
0.6, right? Now let me ask you all a question. Javon, if my graph was like this, you think that would work? Or it needs to occupy most of the graph, most of the space on the graph paper?
Most of the space here.
Exactly, most of the space. So Javon, try to help me come up with a scale. So how much blocks do we have? I have 17 blocks. And I need to represent 0.60. So here what Javon, let me just say 0.60 is like 6, right?
Yes.
If we let one block be equal to just I simplifying things for now, right? Right, Javon? So think of 0.60 as if it was 6. And so if I let every one big block be 1, how much blocks would I occupy?
6.
But how much blocks do I have altogether?
17.
17, so that can work. So the next thing I might look to do, I might look to scale it up. So if 1 represent 1 didn't work, what's the next scale I could use?
2 blocks.
2 blocks represent 1. Good. And in that way, you would occupy how much blocks?
12.
12 blocks. Good. So we'd say that this is 0.10. What would this be?
0.20.
What would this be?
0.30.
This?
0.40.
This?
0.50.
And this last one will be 0.60. You could keep going if you want, because most likely we're going to extrapolate our graph. And this could be 0.80. Good. Adil, if you're genuinely confused, talk to me. I'll try to explain how we came up with that scale.
I think that's it. Understand.
Understand? Alright. Guys, can I use a scale where I say like every 3 blocks is 1?
No.
No, I cannot do that. I cannot do that. Cannot. Right, let's so Adil, I'm gonna let you help me with the scale for the y-axis now. So on the y-axis, what's the biggest value we had to go up to?
2.43.
2.43. How much blocks do we have here? So here what? Let me just say like 2.43, that's approximately 3, right? Maybe. How much blocks we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Alright, so Adil, we have 19 blocks, right?
So,
Now, Adil, if I say every one block is 1, do you think that would occupy enough space?
yes.
No. So let me explain that again. So the highest value we have to go up to is 2.43. 2.43, if we real rounding it off, that's approximately 3. I give you a real rounding it off. 2.43 is approximately 3. So here we're saying, right, Adil, if we say one big block is 1, that would only occupy this amount of space. Is that occupying enough space?
No.
Okay, so what's the other scale I could potentially use? If if 1 to 1 didn't work, what we could look at next?
1 to 2.
2 to 1, right? So let me see if that will occupy enough space. So 1, 2, 3 that occupying enough space?
No.
Nah, where's our other skill we could look at?
3 to 1.
Nah, no. You cannot use 3 to 1. I'll know that, right? You cannot use 3 to 1. Are y'all aware of that or no?
No.
Yes, sir.
Adele, now you know you cannot use 3 to 1. Can anybody explain why? Do y'all know why you can't use 3 to 1? Let me explain something, right? If you use 3 to 1, how are you going to find a definitive scaling for these small blocks? Let me ask you that question. At 3 to 1, that's 0.333. Is that a nice decimal to work with or a really ugly decimal to work with?
Ugly decimal.
Ugly.
Yeah. You don't want to use that number at all, right? You might want to use 2 to 1, that's a half 0.5. You might use 1 to 4, which is 0.25, but you don't want to use 3 to 1 because that would give you a recurrent decimal.
Yeah.
So you don't use 3 to 1. Alright, so Adele, if 3 to 1 didn't work, where's the next one you're gonna look at?
4 to 1.
4 to 1. Let me see if that will work. So this is 1. This 2. I'm still so happy with that. I feel like we could occupy more space. So where's the next one we could jump up to?
5 to 1.
5 to 1. Let me see how that will go. All you feel about 5 to 1? All you feel okay about that?
Yes, sir.
Yes, sir.
Now Adil, you see how about telling you can use 3 to 1?
Yeah.
You can't really use you can't use 6 to 1 either. You can't use 7 to 1 either. Anybody can tell me why saying it we shouldn't use 6 to 1 or 7 to 1?
Because there will be a recurrent fraction.
A recurrent decimal.
Decimal.
And we don't want to deal with that. You're looking for nice even ones like 2 to 1, 4 to 1, 5 to 1, 10 to 1. But 10 to 1 is ridiculous. Everybody okay with how we're figuring out the graph?
Yes, sir.
Javon, Aidan, Adil, Shiloh, everybody okay or no?
Yes, sir. Yes, sir.
Yes, sir.
Alright, so we decide to use 5 to 1. Alright, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Cool. Now we need to figure out what these smaller increments are. So Adil, how much big blocks we have here?
5.
5. So we have 5 big blocks is equal to what?
1.
1. So how would I find for 1 block?
Divide by 5.
Divide by 5. So 1 block would be 1 over 5, which is
0.2.
right. So that's what 1 big block would be. So 1 big block is 0.2. So that'll be 0.2. What is it going to be?
0.4.
So on and so forth. 0.6, 0.8. Right, cool. Now we need to figure out what one of these smallest increments could be. So Adil, how much small increments we have that makes up 1 big block?
5.
Right, so 5 small increments. And that makes up 0.2. So how would I find for 1 small increment?
Divide by 5.
Right. What's 0.2 divided by 5?
0.04.
Good. So so like the smallest increment is going up by 0.04. Do you all understand that or no? Javon, tell me if anything confusing you at all.
No, sir.
Alright, Aaron, are you confused by anything? Aaron, your mic real messing you up, boy. Uh, Shiloh, you alright?
Yes, sir.
Okay, well, let me start plotting now. We start plotting. So, Adela, way out, I'm gonna plot the first point. Pressure there. What happened? Right. So let me start with the first point. So the first point is 0.1, 0.42. So Adel, I'm gonna go by the 0.10 and I'm gonna move up till I reach what?
0.42.
Good. So 0.10 is here and I'm gonna go up to 0.42. So this is 0.4, yeah?
Yeah.
Okay.
It's
What
in
was
the
it?
middle of the small block.
Yes, the middle of the small block. Can anybody explain why Adel said the middle of the small block?
So because one small block is 0. Okay, one small block is 0.04, and we're looking for 0.02, which is half.
Yep, that's it. So good job. So in physics, you go into parallel dot, and around dot, you go on parallel circle. If you want, you can also par x. I prefer the dot. Right? Shiloh, let's do 0.20, 0.81. So I'm gonna go on. I'm gonna move over to what's on the x-axis.
So 0.20
Right? And I'm gonna go
and
up to
0.81.
this is 0.8. So I'm gonna do what?
Uh, a little under half of 0.8.
Like right here.
Yes,
All right, Javon. Now I help me with the other one. So Javon, I'm gonna move to what on the x-axis?
0.3.
0.2,
0.3.
0.3. Right? And I'm gonna move up to what?
Uh,
So in this instance, Javon, I know we had say every 5 to 1, right? We had say that, yeah?
yes, sir.
But that kinda hard to use that because a lot of it is kinda empty, if you know what I mean.
Yes, sir.
So if you want, you could continue this throughout the graph. It will take more time, but it might make your job a little easier. So let me continue it. So what would that be? Remind me, Javon, what was one big block? What was one big block?
0.2.
0.2. So that would be 1 point.
1.2.
This would be
1.4.
right. I want speed like semi-automatic. Go. 2 point. Speed, speed, speed.
2.2. 2.4. 2.6. 2.8.
Good. So we want to go up to 1.21. Tell me when to stop. Ah, Javon.
Don't wanna be
1.21. 1.21, right? Come on to stop. 1.21.
stop. No. Stop. A
Yeah,
bit low.
I should stop right here. Should a little lower. But in the grand scheme of things, it really matter, you know.
Yes, sir.
Alright, the next one is I'm gonna go on what's on the x-axis.
0.50.
Um 0.50, yeah? And I'm gonna go up to what?
1.99.
Where would that be, boy? So this would be what? Remind me, Javon, what was that? What was like the smallest block equal to? The smallest block?
0.04.
Nah, the smallest block was 0.04. The smallest block was 0.04. So this could be 1.8 what? Javon?
Yes, sir.
Tell me if you're having any problems.
1.84.
Alright, that'll be 1.84.
1.88. 1.92. 1.96.
Aha, so then 1.99 might probably be somewhere over here. And tell me if you follow.
Yes, sir.
So that's gonna be right here. Then we have 0.60, 2.43. So I'm gonna do this one, and I want to let you tell me if it's correct. Are you think that correct or that wrong?
No, sir.
That wrong?
Yes.
What about so the objective is 2.43. Let me know if that's right or that's wrong.
No, sir. Like a bit below.
What about you all? Do you agree or no? He says a bit below.
Yes, sir, but
A bit below, why?
because it's not exactly 0.4.
Exactly. Good. I'll leave lose marks for that if I'll pay it exactly at 2.44. So that'll be right here. Alright, let me know if you're okay with that.
Yes, sir.
0.6, 2.43. Right. So now you're gonna take your ruler, you're gonna line it up. Now this specific graph cuts the origin, it passes through the origin. So we want to make sure everything is aligned as much as possible. But it needs to pass through the origin. I'm not gonna use your ruler. Yeah, I feel like that's pretty decent. You okay with that?
Yes, sir.
Now, if you zoom in close, you'd notice that some points are to the left, and some points, well, are below. You want to make sure the distance between them are kind of even, and that's because you want to create a what do you call it? You all should know the name. You want to do a what type of graph? That would be
That's good.
best fit, right? If I did something mad like this, do you think it'd be acceptable? Watch. No.
Listen.
In the best fit line, your line needs to sort of be in the middle of the data points to be an average, because the best fit is essentially an average of the data you collect. Nice. So now we would have to find a gradient. Javon, what's the easiest point here to use from a gradient? What's one of the easiest points? See if you can spot the easiest point. It's a very, very simple point I could use. If you all see the easy point, tell me. But it's a very, very easy point you could use. I said that this graph has to pass through what? Tell me guys, this graph had to pass through what?
They're the origin.
Had to pass through the origin, so that's our point. That's I can't think of an easier point on it. I can't. I literally can't. It's like the easiest point you could pick. Alright, time for me to read off another point. So let me look for a nice point we could use. Guys, I don't really see any nice points, you know. Actually, by that point, like real close, it's typically advisable to take 2 points that are kind of far apart from each other. So like when I was in school, here's a little ratchet I used to do, right? I had a clear ruler. Any of you have a clear ruler?
Yes, sir.
And what I used to do, right? I used to align my ruler so that when I draw the line, I know it's gonna pass through some nice points. That's the ratchet I used to pull. So, like, let me show you what I mean, right? I would have take my line and I would have draw it so it passed through some points for sure. So like, you see how I just moved that? Now I have this point to work with. That's the ratchet I used to pull. So Javon, here what I used to do, right? I used to take my clear ruler, and before I draw the graph, I used to make sure it aligned and it passing through some nice places. You understand the hack?
Yes, sir.
And so when I draw my line, I already know where I could read it off from. I wouldn't have to go looking for points. But anyways, Javon, help me read off this point. So what's the x value?
There's
What?
0.0.
0.0? I'm talking about this one here. Look at it carefully.
0.55.
0.55, yes. And now we need to read off this. What does that look like?
2.24.
2.24. Does it matter which one I label x1, y1 and x2, y2?
Yes.
Yes, sir.
Right. It doesn't matter, but logically I should label this x1, y1 and I should label this x2, y2. Nice. So, you know how to find gradients or no?
Oh, yes, sir. Yes, sir.
Oh, well, let me do that fast. Now in physics, gradient is typically be like a 5-mark question. Now they're giving you so much marks because number one, they want to see the formula. So you have to write the formula for gradient first. What's the formula for gradient?
Y2 minus Y1 over X2 minus X1.
Right, then they want to see substitution. So we label this x1, y1. We label this x2, y2. Again, it does not matter how you label it, so long as you do it correctly. So y2 is 2.24. What's y1?
0.
What's x2?
0.55.
What's x1?
0.
Alright, so plug that into your calculator and let me know. So let me know what you guys get. 2.24 over 0.55.
4.0727.
What y'all get?
4.07.
Anybody else could confirm they got that? 4.07.
Yes, sir.
Now we need to look at the units, right? If you don't put your units, you lose our mark instantly. So y2 minus y1, that's on the y-axis. Right? So that's on the y-axis. So what are the units on the y-axis?
Second square.
Second squared. So I'm going to put second squared here. And what are the units on the x-axis? Meters.
Yeah.
It's going to be s squared slash meter. Is anybody confused by that? Adil, let me know if you're confused by that.
Yes, sir.
Okay. Okay, so here what? This graph was for a pendulum. Now you could use a pendulum, the experiment of the pendulum, to find for the gravitational field constant, G, gravity. What do you all think gravity is? G. What is G? 9.8110, so on and so forth. And that one is fine. So let's use this to find for gravity. So this is a gradient here. So again, here what I'm saying, guys, for the pendulum experiment, you could use this to find for the gravitational field constant G. Do you all remember how the pendulum experiment went?
Yes, sir.
Yes, sir.
Right. So, cool. Is there anybody confused? Remember, like, this is what the pendulum experiment looked like. You had a retort stand, you clamp a piece of thread or something here, you put a bob, you displace it and it swing back and forth. Sheila, you remember how I went on the website and we looked at how length and mass would affect it?
Yes, sir.
But truth be told, what was the only thing that affects the period? Is it the mass or is it the length?
The length.
The length. The length is the only thing that affects it, not the mass. But anyways, let's find for G using this. So G is going to be equal to 4 pi squared multiplied by 1 over the gradient. What do we find the gradient to be?
4.071.
Alright, plug that into your calculators and let me know what you're getting. If it's correct, you should get something around 9.810, something around there. It might be a bit lower, but that's fine.
9.70.
Sir, 9.70.
Yeah, 9.70, and the units are going to be what?
Meters slash seconds squared.
Badness. Alright, so everybody okay with that?
Yes, sir.
Nice. So if I find a graph question and I give it to you all right now, do you all think you could handle it?
Yes.
I hear Shiloh say yes. Javon, you have graph paper with you right now or no?
No, sir, not right now.
You feel like you can get graph paper right now or not?
I don't think so, sir.
Oh. Adon, Adil, can you all get graph paper now?
No.
Well, you don't have graph paper, boy. I'll come to physics class. I must have graph paper, boy. Well, I'm gonna look for a question for you all. Here's a question. Let me just verify something. Yeah, go ahead and try this. Give this question a go. Actually, this question might take you all quite a while to do. I feel like the best course of action is to do it with me. Because, like, if you, it could take quite a while, to be honest. So, best we do it together.
Yes.
Alright? So, let me just give it a go, right? Shiloh? Get the question right from her.
Anya performs an experiment to measure the acceleration due to gravity, g. The time taken for 20 complete oscillations was recorded as the length L of the pendulum was varied. The results are shown in the table below.
Okay.
Okay. Time taken for 20. Continue.
Yeah, continue.
Okay. Time taken for 20 oscillations. TS 15.5, 20.1, 23.7, 26.9, 29.8, 32.4. Length L slash M 0.150, 0.150, 0.250, 0.350, 0.450, 0.550, 0.650. Period TS 0.775. T squared slash S squared 0.601.
Alright, so, I have a question. They're saying time taken for 20 oscillations. Anybody could remind me why it would take the time for 20 oscillations? Why not just measure one oscillation and done?
For less error.
What? Yeah, let's specify. What type of error? What's the name for the error?
Sir,
Human
human.
reaction time error.
Yes, human reaction time error. That is it. Cool. So, let's figure out the period first. So if this is the time taken for 20 oscillations, how would I find the time for one oscillation?
Sir, divide by 20.
I'd have to divide it by 20, yes. So there we go. Alright. One moment. Alright, cool. So we're gonna say 20.1 and we're gonna divide that by. Tell me, guys. 20.1 divided by
20.
20. So 1.005. Adil, how am I going to figure out the period for this here?
period for
So the period for here.
yeah, the square root the
Nah, I wouldn't square root.
divided by 20.
Where was you on in? Yes, that's correct. Because Adil, this is the time for 20 oscillations, you know. You want to find the time for one period, which is one oscillation. So you would say 23.7 divided by 20. That's 1.185. You okay with that or not?
Yes, sir.
Then we had 26.9. Let me just work the others fast. I think we get the idea now. 26.9. 1.345. Then we have 29.8. 1.49. Are you confused by anything I do in here? Let me know if you-
No, sir.
Alright, so Adil, tell me, how am I going to figure out t squared now? What to do?
Yeah, to square all of the numbers you just write in.
Correct. So that's going to be 1.005 squared. Now, here what? When you look at all of the things you're putting in, it's how much decimal places?
3.
3. So we're going to round it off to 3 decimal places. Because that's the degree of accuracy. So what will that be? If I round it off to 3 decimal places, what that will be?
1.010.
Correct, 1.010. Right? And this one over here.
One point zero four 1.404.
Right? Then that's going to be 1.345 squared, which is 1.809. Then we have 1.49 squared. 2.220, and then 1.62 squared, which is 2.624. Alright, have anybody confused? Like scratching their head? I'm scratching my head right now, but I don't mean I'm confused, but anybody else scratching their head?
What's that?
No, sir.
So that's an easy 6 marks, or what do you think?
Yes, sir.
Yeah, I think that's a real easy 6 marks. You gotta get out 6 marks. Now they want you to plot a graph of t squared against L. So tell me, Adil, which one goes on the y-axis? T squared or L?
T squared.
T squared, good. You learn your lesson, right? This going on the y-axis and we're going on the x-axis.
L.
L. And I'm going to use this scale. I want to use the scale that CXC just give you. So, 1 second. Who wanna help me come up with a scale? Do I have any takers? Finally moving real quiet today, you know. What's going on, guys? This early morning thing killing all here. I realize it, you know. The early morning
Yeah.
vibes killing all here. Don't worry, killing me too. It's be hard to roll out, get up that bed, you know. It's be hard. Javon, what time you just wake up?
What time I usually?
Yeah, like, well, for lessons this morning, what time you wake up?
Say like 9.
You wake up 9 o'clock.
Yes.
So you wake up just now.
Yes, sir.
Oh, and that yes. You wake up just in time. Optimizing that sleep. At what time you want to sleep?
Say like 12.
Don't feel shame on thing, you know, I went to sleep 4 o'clock. I feel like I feel shame. What? It's fine, it's
Say
fine.
like 12, sir.
12? That early? Nothing wrong with that?
Yes, sir.
Yeah. Alright, so let me jump straight into this. So here what Adil, I want you to tell me the first point. What's the first point?
This point is 0, 0.15 and
Nah.
0.
Oh wait. Yeah, you're going good. Yeah, sorry about that. Yeah, 0.15.
0.15 and 0.601.
No, Olia, let's be realistic. Do you think we'll be able to like show three decimal places on our graph or two decimal places? Like what do you think? Think
No,
logically.
sir.
Say that again?
No, sir.
Nah, so like what I gonna do, right? I gonna round up everything to two decimal places. For the graph's sake. So my first point, I'm gonna put a little y by t squared and I'm gonna put x by l. So my first point is 0.15. Come on, what Adil? And I'm gonna round up everything to two decimal places. So what that will be, Adil?
0.60.
Right, 0.60. Where's my next point?
0.25.
0.25 and 1.01.
0.25.
And 1.01.
Right, next one.
0.35 and 1.40.
Right, then we have 0.45.
1.81. 0.55 and 2.22. 0.65 and 0.62.
Yeah, sure. I see in 2.6.
2.62. 2.62.
Right. So Adel, you gonna help me come up with the x-axis scale, and Javon, you gonna help me come up with the y-axis scale. But I don't think y'all should have any problems. So Adel, what is the biggest value I had to go up to on the x-axis?
2.62.
On the x-axis, eh? On the x-axis.
0.65.
0.65. Alright. So 0.65 and that's approximately like, well, that's 0.7, right? But let me just call it 7. You with me? So
Yeah.
here was another 0.65. That's approximately 0.7, right? But I could treat that as if it was 7. Okay. Now how much blocks we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 17 blocks, right, Adil? Yeah?
Yes, sir.
And Adil, okay, we had to go up to 0.65, which is approximately 0.7, and we could essentially call that 7. Now Adil, if I go to say one block is 1, I would occupy enough space.
No.
So what's the next scale I could use other than that?
2 blocks is 1.
2 blocks is 1. Look, we get 1 time. So I'll call this what?
1.
Remember, is even though our saying is like 7, is really 0. What? It was 0.65. So I will say every 2 is 0.
0.1.
Right, 0.10, then it has 0.20. Right, oh my days, stop that. Yeah. So far, would any of you guys have any trouble figuring out what's going on the x-axis, the scale? Do you have any problems here?
No, sir.
No. Of course, we need to, what else we need to do over here,
No, sir.
Adel?
Find out how much one small block is.
Say that again?
We'll find out how much one small block is.
Yeah, one small. Well, actually, that's not wrong, you know. That's not wrong. But what we should do is we should probably label the axes. They always want to see that. That's part of your marks, eh? I do gotta label the axes. So, tell me what does the x-axis represent?
L
L, and that's measured in what units?
meters.
Meters. Yes. So, are you okay with all? Are you confused?
Okay, sir.
Okay. Javon, it was you who asked help me with the y-axis, and
Yes, sir.
alright, so Javon, what we had to go up to on the y-axis?
Sir, 2.62.
So that's approximately what?
2.7
Well, if you run it up to the nearest whole number, what do you think that'll be?
or 3.
3, right? No problem, that's 3. Bet. Nice. Now let me count how much blocks we have. Well, before we even do that, let me just think about it, right? Javon, you feel like every 1 unit is 1 could make sense?
No, sir.
Nah, that don't make any sense at all. So what could look at next?
There you could look at 2.
Nah, we gotta go a little bigger. Yeah, keep going.
They could use 5. Sir.
1, 2, 3, 4, 5. Let me see that will work. Even that, but it depends on how the graph was given, eh? Sometimes CXC just give different graphs. So it really depends on how the graph was presented to you. Okay. Because you can't do 6, you can't do 7. 8 is a possibility. But who really uses 8? So hey, this makes the most sense, right? And again, it depends on the type of graph CXC gives. Sometimes CXC go bring a graph like this. Sometimes it might bring it like this. You know what I mean? But this look like the best option. Right. So some of fast. Well, actually, we could save some time. Let me copy and paste something real quick. I feel like I could just copy and paste this. Nah, I don't think that will work. I was really trying to pull some smart man antics, you know. Save some time. Oh well. Yeah, so we'll call this 1.00. We already do this, right? So Javon, every big block is what?
0.2,
Next one?
0.4, 0.6, 0.8.
So on and so forth. This is 2.00. This is 3.00. We're gonna label the axes what?
Pi. Well,
That'll be t squared s squared, right? Because it was
yes, sir.
t squared versus L.
Yes, sir.
And now we need to figure out what like the smallest block is equal to. What is the smallest block equal to?
0.04.
There we go. So my first point is 0.15, 0.60. Tell me if this is correct. Are you looking like it? What do you think?
Yes, sir.
Right, so you understand that?
Yes, sir. Yes, sir.
Okay, next one is 0.25, 1.01. So let me do that one. So 0.25 between 0.20 and 0.30 and 1.01. That will be right here. Let me know if you understand that. You okay with that? Tell me if I agree with that or not. 0.25, 0.01. Yeah, no, maybe.
Yes, sir.
Alright, next one is 0.35, 1.4. So 1.4, that looking like it will be over here. Anybody confused though?
No, sir.
Okay. Then we have 0.445, 1.8, 1.81. So 4, 6, 8. Are they okay with that or nah?
Yes, sir.
Are they want me to
Yes,
put
sir.
in? Are they want me to put in small increments or leave it out?
No, sir.
Leave it out, sir.
Leave it out. Okay, no problem. And then we have 0.55, 2.22. So 2.2 would be over here and 2.22 right here. Yeah, how you feeling about that? Because, you know, this is 2.2 and, well, every small block is 0.04, so 2.22 will be
Yes,
like,
sir.
right, cool. Then 0.65, 2.62, 2.62, so 246 right here in the middle. How we feeling about that? That was an easy graph, or
Yes, sir.
now? Now this graph had a pass through the what? What this graph had a pass through?
Origin.
Right. This graph has to pass through the origin. So let me line up the graph as such. Well, remember the hack, right? Anybody can remember what's the hack?
Up.
Well, I had to say ratch. Yeah, where's your ratch?
Uh,
We boy, I'll let make your life easy. Watch. So before I draw my line, I'm gonna take my ruler and I'm gonna make sure the lining up with some nice points. Right? So 0, 0 is always a bet. Well, that's a nice. Yeah, boy, that's a nice one. Are you seeing that?
yes, sir.
Yes, sir.
Yeah, man, we go work with this. Go work with this. Alright, so my first point is what? What's my first point? What is the easiest point I could pick for these type of graphs?
Here.
Yeah, man. I wanted to pick another point. We have plenty nice points.
0.60.
0.60.
Yeah.
0.60 what?
And 2.4.
Well, I agree with someone. He's saying
Yes, sir.
saying 0.60, 2.40. Yeah, I would agree. Badness. So we could probably label 0, 0, x1, y1, and we could label the other one x2, y2. Nice. Now here what's it? And this is a place where students lose marks. I wasn't going to read this from her. Oh wait, before we finish, I want you all to tell me what is missing from our graph. What is missing from our graph?
Title.
A title, and you're supposed to put the what else? Start with S.
Here, the scale.
Supposed to put the scale. So this will be the graph of t squared versus L. Are you alright with that? And the scale now. You can say every 2 centimeters is equal to what? I'll do the x-axis first. 2 centimeters is equal to what? Every 2 centimeters is equal to what, guys?
0.1.
Right. This is a place where students lose marks. 0.10 what? What? What's the units? 0.10 what?
Meters.
Right. Meters. Yeah. Cool. Now, let's look at the y-axis now. So on the y-axis, what was the scale we had used? No, and I know we put like small divisions and thing, eh? But generally speaking, what was the scale we had decide on?
5 to 1.
5 centi
5 centimeters is equal to what?
1
1.
second.
Second squared. We
Yes,
okay with
sir.
that or not? And you had to specify, right? So 2 centimeters on the x-axis. So this is the scale. That's what you had to do to get full marks. So is our graph taking up most of the okay, is our graph taking up most of the page?
Yes, sir.
Do I have a title?
Yes, sir.
Yes.
Have I labeled marks?
Yes, sir.
Do I have the scale?
Yes.
Yes.
Cool. Now, all right. So we have 16 marks in the bag, guys. 16 marks, real marks. Nice. Then we see in here determine the slope s of the graph. When they say determine the slope, slope is another word for what?
Gradient.
Did you all know that?
Yes.
Adil, did you know slope is another word for gradient?
No.
Well, now you know. Right? So slope means to find the gradient. Now, what's the formula for gradient?
y2 minus y1 over x2 minus x1.
Now, depending on how dreaded the teacher is, you'll actually lose a mark if you put that equal to m. You'll actually lose a mark if you put that equal to m. They said it was equal to what in any question? They said the slope what?
S.
S. So you're gonna call that S. And you want to put down your points that you're going to use. This is advisable. Put down your points that you pick from the graph. 0, 0, label it x1, y1. And you want to put the other point to use. I think it was 0.60, 2.4. Was it? Yeah.
Yep.
0.60, 2.40. So x2, y2. Then the next step is to substitute. Hey, you're getting marks for the formula, you're getting marks for putting the points, you're getting a mark for substituting, and you're getting a mark for getting the final answer. And you need to put the units as well. If you notice, they said and what? They said and included
Yes.
units. Remind me, the y-axis, what's the units on the y-axis again?
Seconds.
And the units on the x-axis.
Meters.
Great. So what's that going to be?
Be 2.40 minus 0.
Mm-hmm.
And 0.60 minus 0.
Alright, so plug into the calculator and let me know what you're getting.
Uh, 4 meters per second.
So you're getting that? 4 meters per second squared. Hey, whoa. Meters per second squared. No. S squared per meter.
Yes, sir.
If you had put meters per second squared, you lose a mark there, you know. Instant lose mark. Right? Because it's S squared on top and meters on the
Yes.
bottom. Adil, let me know if you're confused or if you understand.
Yeah, you go through that part, are you?
Which part?
Like, like how you find the gradient.
Okay, no problem. So, do you know how to find gradients?
Y2 minus y1 over x2 minus x1.
Good. So to find the gradient, you need 2 points on your graph. 2 points that are on your graph. Now, Adil, you cannot take any points that you use here. You see how we have these points here, Adil? You see them points, Adil?
Yeah.
You cannot use that. You cannot use those points. Understand? Because this is our best fit graph. So you need to plot those points, do your best fit, and read off the points from the graph itself. For our graph of t squared versus L, the easiest point to pick is 0, 0. I have that point for sure. So I have 0, 0. And then you're looking for another nice point. I see this point here. It's a nice point. That's 0.60, 2.4. Because 0.60 here and 2.40 over here. You understand?
Yes, sir.
Right, so the first thing you want to do, you want to put on the formula for gradient, and you have to be careful. They call the gradient what here? What are they calling the gradient here?
S.
S. So you put on S is equal to y2 minus y1 over x2 minus x1. And while you're at it, I want you to put down the units on the y and the x axes. What is the unit on the y axis?
S squared.
Right. So I'm gonna say s squared on top, and then in the bottom, meters. Right? Because we're measuring length in meters on the x axis. So that's all they had to do. Watch. 2.40 minus 0 over 0.60 minus 0. And here your answer. Tell me if it have any part in particular that confusion you.
Yes, sir.
You sure you're right?
Yes, sir.
Okay. How about the rest of you guys?
Yes, sir.
Yes, sir.
Cool, yeah. So let's answer part D now. Now in part D, they're giving us a formula that has S and G in it, and they want us to determine acceleration due to gravity. So what do we have to make the subject of the formula here?
G.
Do you all agree that we have to make G the subject of the formula?
Yes, sir.
Good. Now do I know what S is?
Yes, sir.
Right, so what I could do then? If I know that S is 4, what I'm gonna do?
Substitute.
Right, so I can say 4 is equal to 39.4 all over G. What next? Guys, this is just maths from this point onwards. Not enough physics, it's just maths. Any suggestions?
Yeah, you multiply the 4 times, bro.
Say that again.
5.
I heard multiple things. So, here what? There's two ways you could do this. Are you all familiar with cross multiplication?
Yes, sir.
Yes, sir.
Alright. I could write 4 as 4 over what, Adil? Adil, tell me, what could I write 4 as? 4 over what?
G.
So I could write it as 4 over 1. Because, Adil, what's 4 over 1? Plug that into your
4.
calculator. 4, right? So I could write 4 as 4 over 1. Since I have a fraction on either side, I could now cross multiply. And if I cross multiply, Adil, tell me what I'll get. Alright, tell me.
300 39.4 minus 4G equal to 39.4.
Yep, that's it. 4G is equal to 39.4. So how would I find for 1G?
Divide
Divide
by
by
4.
4.
Right, I would divide by 4 on both sides. So what is 39.4 over 4? Anybody? Guys, I'm leaving my hanging here, buddy. 39.4 over 4, what's that? What's that? Anybody? Shiloh, Javon, Adel, Aidan? Are they hearing more or no?
9.85.
Right. Are they was hearing me the whole time or like, are they was hearing me?
Yes, sir.
And now we're just staying quiet. What kind of thing is that? Javon, did you have a hard time plugging this into your calculator? Or
No, no, sir.
I find when they was staying real quiet, I was like, what's going on? Okay, where's the units for G? Add up the units. Tell me, where's the units? What are the units? Anybody want to tell me the units? It's gravity. Again, why be so quiet? Yo, people. Sheila, where's the units for G? Can I hear any Sheila? Javon, where's the units for G? Gravity. Acceleration due to gravity. What's the units for acceleration?
Per second.
Yes, meters per second squared. And there's another way you could understand this. Let me explain. So S is equal to 39.4 all over G, right? Something you could also do, you can multiply by G on both sides. You'll end up with SG is equal to 39.4. And then you could divide by S on both sides. When you do that, you'll end up with G is equal to 39.4 all over S. Now, what were the units for S? The units for S was S squared slash M. It was S squared slash M. So here's the thing. The 39.4 over 4, that would have given us 9.85. But you have 1 all over S squared slash M. So if you have 1 over S squared slash M, it's going to invert. And that's going to turn to a meter per second squared. Because it's 1 all over S squared slash M. This would turn to a meter slash S squared. Right, but guys, remember, acceleration is always meter per second squared.
That's
A little real quiet, a real concerned. I'm very concerned. What's going on? Javon, everything alright?
Yes, sir. Yes.
But I find it real quiet. What's going on? You sleepy or something? You had to get food? You sound like you're hungry, like you need to eat some food. That could be it, you know, Javon, you hungry?
No, sir.
I hungry, eh? But anyway, you hungry? Because Javon, like, you just wake up for class at 8, 9 this morning. Are you not hungry or anything?
Yes, sir.
Maybe that's why they're not talking so much. But let me know if you're confused by D. Adele, let me know if you're confused by D.
No, sir.
Yeah, 100% sure.
Yes, sir.
I'll just saying yes sir and thing, you know, but the trust issues, man. The trust issues. I'm not sure if I could trust all you. Yeah. But that's a whole question there we do. For scientific method, pendulum experiments. Nice. So, okay. Let me move on. Before I move on, I feel like we should do these questions. Right? I really feel like we should do these questions. Because this over here tests your knowledge on units. So I'm gonna let Javon help me with this. Javon, read that question for me.
Daniel wants to determine the density of steel. He measured the mass of 10 steel marbles. He measured the volume of the 10 marbles by placing them in a measuring cylinder filled with 50 centimeter cube of water. His findings are listed below. Mass of 10 steel marbles equal 336 grams. Initial volume of water in measuring cylinder equal 50 centimeters cube. Final volume of water in measuring cylinder equal 92 centimeters cube. A. Explain what is meant by the term density and state its SI unit. B. State the mass of one steel marble in kg.
Alright, before we continue, do you all know what density, the formula for density is or not? Density. Do you all know what density is?
No, sir.
Was it you guys that I did Archimedes principle with? Nah, I fed out my Form 5 class. But do you all know what density is? The formula for density.
Oh, mass over volume.
Mass over volume. Great. Javon, you know that or no? Adon, you know that? Density. Mass over volume.
No, sir.
Nah? Alright, well now you know. So the symbol for density is this symbol over here. And it's pronounced as rho. Like row your boat. Rho. And it's mass all over volume. Let me check something. Right, so masses are common, eh? As I always mixed up. Yes, so density is equal to mass over volume. Can anybody remind me what the SI unit for mass is?
kg.
kg, what's the SI unit for volume?
Meters cube.
Meter cube, nice. Right, so Javon, they say in Daniel wants to determine the density of steel, right? He measured the mass of 10 steel marbles. Maybe that might be important. They say in 10 steel marbles. He measured the volume of the 10 marbles, and he measuring volume here by placing them in a measuring cylinder filled with 50 centimeter cube of water. So, Javon, initially you had a measuring cylinder, right?
Yes, sir.
And you have how much water in it?
50 centimeter cube.
Now, question. When you drop the steel balls into the measuring cylinder, what would happen to the water level? Logically,
Alright.
it's gonna rise to some new level.
Yes, sir.
And what did it rise to? The same final volume of water is 92 centimeter cube. So, Javon, I want you to think logically for me. What do you think the volume occupied by these steel balls are?
They're 42 centimeters cube.
Exactly. Because when you introduce the steel balls, the volume rised by 42 centimeters cube, meaning it added 42 centimeters cube of space. It occupied that volume. So do you understand that?
Yes, sir.
And is that the volume for one steel ball?
No, sir.
How much is
For
that?
all of them. For the 10 of them.
10 of them. Adil, let me make sure we understand that. Adil, if you drop steel balls in a measuring cylinder, what would happen to the water level?
Here rise.
It would rise because the steel ball is gonna occupy what? What are they gonna occupy?
Volume.
Exactly, they're gonna occupy volume. So Adil, if before it was 50 and after you add it is 92, what's the increase in volume? Like how much did it increase by?
42.
Exactly, and that would tell you the volume of the
Steel balls.
exactly the volume of the steel balls. Great. Nice. So I hope you understand that. You good?
Yes, sir.
Now Adil, is that the volume for one ball? I mean one marble or tell me.
That is the volume of 2 marbles. So the volume
Nah,
of one will
nah, no,
be
not two, not
what?
two. I just put out there for explanation. Let me make it correct. Right? Because it's 10. It said 10 marbles, right? 10 marbles. So that'll be the volume occupied by
10. So one will be 4.2.
correct. Right? So I like how we thinking here. This is good thinking. So 10 marbles is equal to 42 centimeter cube. So one marble is equal to 4.2 centimeter cube. Javon, you following the logic so far?
Yes, sir.
Right. They're telling us the mass of 10 steel marbles is 336 grams. That's the mass for how much?
10 steel marbles.
10. We should probably find for.
1.
Right. So let me do that. 10 marbles. 10 marbles is 336. So one marble will be what?
33.6.
Alright, so explain what is meant by the term density. So density is just the mass per unit volume. That's all. That's all. That's really it. Right? So it's just the amount of mass in a volume. Right? So that's actually it. So I'll just put the definition here. It's simply the mass per unit volume. So Javon, in other words, how much mass is packed in a given volume? That's what it tells you. So if I tell you
Yes.
something has a greater density, that means it's like more packed. The molecules is a lot more packed together. If that makes sense. So let me explain. Imagine you had this cube over here, and you make it using paper, right? And let me just say you make a cube in the same that has the same size out of metal. Which one would weigh more? The paper cube or the metal cube? Keep in mind it's the same size, same volume they're occupying. Which one would have a greater mass? The paper cube or the metal cube?
Metal cube.
Right. And I'm telling you, both of them occupying the same volume, same volume. The only difference is both of them have different what?
Density.
Different densities. Right? Different densities. Because paper would weigh a lot less than metal, you understand? You sure you understand that?
Yes, sir.
Right, the mass per unit volume, you can put the formula here. Density is equal to mass all over volume. They want the SI units. So the units for that, you tell me, Javon, what do we measure mass in?
kg.
And it's over volume, so that'll be kg per what?
Meters cube.
Nice. Everybody okay with that?
Yes, sir.
Easy 3 marks. Okay. Part B. State the mass of the one steel marble in kg. So what is the mass of one marble in grams?
33.6
But they want the answer in what?
kilo.
Kilograms. So what we gotta do? If you want it in kilograms, what we gotta do?
All right, you'd have to divide by 3. I mean, 1,000.
Divide by 1,000, yes. Right? So if you want to go from if you're going from grams to kilograms,
Move 3 points.
right, you gotta divide by 1,000. Or move 3 points. 3 points to the left. Right? So that's gonna be to the 3.6 divided by 1,000, and what are we gonna get?
0.0.
0.336.
Right? So you should get 0.0336. Are they getting that or not?
Yes.
Right, so Adil, be honest with me. You understand what happening so far or not? Adil?
Yes, sir.
You sure you understand what happening so far or not?
Yes, sir.
Alright. Javon, read part C for me now.
State the volume of the one steel marble in meters cube.
Right. In meter cube. You gotta be real careful with this one, like so careful. I can't stress how careful you gotta be. So let me ask you a question, right, Javon? How much dimensions does a steel marble have since it's a 3D shape? How much dimensions? 3 dimensions, right? 3.
Yes, sir.
So let me explain something. If we're talking about 3 dimensions, call this dimension Z, X, Y. 3 dimensions, right? 3 dimensions. And each dimension is in centimeters. If I want to get meter cube, wouldn't I have to convert each dimension? I would have to convert each dimension to what?
Meters.
Exactly. I'd have to convert every single dimension to meters. So, first of all, how do I convert centimeters to meters? I would divide by what? How much centimeters make up 1 meter?
100.
Right. So Javon, I would divide a centimeter by.
100.
You sure you understand that, right?
Yes, sir.
Cool. And so that would just work out to be 1 over 100.
Yes, sir.
So 1 centimeter is 1 over 100 meters. And you'll convert every single dimension to that. So each dimension is now going to be 1 over 100 meters, 1 over 100 meters, 1 over 100 meters. So when you want to find meter cube means I got to multiply each dimension by each other. So you're going to end up with 1 over 100 by tell me, Javon. You're going to end up okay, so again it's meter cube. What do you think meter cube means, Javon? Meter cube.
Sure, there are 3 dimensions.
Say that again?
There are 3 dimensions.
Exactly, but it means okay. Think of exponents. Like if I ask you to calculate 4 to the power 3, what that would be? How would you work 4 to the power 3?
36.
How did you work it out?
So 4 3 times.
Alright, you have to be careful, right? So 4 to the power 3, it really means 4 by 4 by 4. Did you know that?
Yes, sir.
And it will actually be 64, because 4 by 4 is 16 and 16 by 4 is 64.
Yes, sir.
So Javon, if 4 cube means 4 by 4 by 4, what do you think meter cube means?
Meter by meter by meter.
Exactly. So this is 1 over 100 meters. I gotta multiply that by this, and I gotta multiply it by this. So by the time you finish, it's going to be 1 over 100 by 1 over 100 by 1 over 100. So that's 1 over 100 cube. So if you want to convert from cm cube to meter cube, you gotta multiply by 1 over what? Tell me, Javon, how would I figure that out? So 1 over 100 cube, what's that? What is 1 over 100 cube?
Sure.
Javon? You know or nah?
No, sir.
Alright. You have a Sharp or Casio calculator?
Casio.
Alright, so in the calculator, we're going to put 1 over 100 to the power 3. And tell me what you get. What are you getting? Javon, you having some trouble plugging that into the calculator? It's alright if you're having trouble, just tell me. I'll see how I can help you. Javon, what's going on? Shiloh, you hear me?
Yes, sir.
Javon, talk to me. Again, Javon, if you're having any problems, that's fine. No, I'm here to help you. Just tell me. Don't stay quiet. Can't help you if you're quiet. Javon,
Yes, sir.
what's going on?
So I got 0.0000001.
A calculator not giving you it in scientific notation.
0 10 10 to the negative 6.
Right, 10 to the power negative 6, that's right. So, you're gonna see 1 by 10 to the power negative 6, right?
Yes, sir.
Let me make sure you understand this thing one more time. Javon, look at the units here. You're converting centimeter cube to what?
Meter cube.
So you have to convert every single dimension to meter. How much dimensions you have to convert since it's 3 dimensions?
3.
3 dimensions. So when I convert, one dimension is 1 over 100 meters, the other dimension is 1 over 100 meters, the other dimension is 1 over 100 meters. By the time you multiply all together, it's going to be 1 by 10 to the power negative 6. So if you want to convert centimeter cube to meter cube, you have to multiply the centimeter cube by 1 by 10 to the power negative 6. So
Yes, sir.
if one marble is 4.2 centimeter cube, I will multiply that by, tell me Javon, if one marble is 4.2 centimeters cube, what would that be in meters cube?
So you multiply by 10 to the negative 6.
Good, and what would that be? Well, that would just be yeah, I'll leave it like that. So when you work it out, one marble is going to be 4.2 multiplied by 10 to the power negative 6 what? What's the units? What's the units now? Javon? What would the units
Yes,
be?
sir.
What would the units be now?
A meter cube.
Right, meters cube. Yeah. Sheila, you understand that we have to convert every single dimension to meter?
Yes, sir.
So, because you have 3 dimensions, that 3D shape. So, to convert 1 centimeter to a meter is 1 over 100 meters, right? And divide by 100.
Yep.
So, it come like you
Yep.
divide 100 3 times. So, divide by 100, divide by 100, divide by 100. Which works out to be 10 to the power negative 6. You're just multiplying by 10 to the power negative 6.
Yep.
Eden and Adil, if all are confused, tell me. Alright, all quiet, taking it, not sure how to take that. But long story short, if you just want to remember it, Javon, if you want to convert 1 centimeter cube to meter cube, you have to multiply by what?
1 over 100.
No, not 1 over 100. Because remember, it's meter cube. So you have to convert every single dimension to meter and then multiply all. So that will be multiplying by 10 to what power?
Negative 6.
Right, because remember, 10 to the power negative 2 by 10 to the power negative 2 by 10 to the power negative 2. Gonna get 10 to the power negative 6. Javon, I feel like you don't fully understand that one. Talk to me.
Yes, sir, I understand, sir.
So you understand you have to convert every single dimension
Yes,
to
sir.
meter.
Yes, sir.
Alright. Cool. Now we're to calculate the density. So tell me, what was the density formula? Javon?
Sir, mass over volume.
Mass over volume. Right. What's the mass? Right, no problem, you're done. Right, Javon, what's the mass in kg? What's the mass in kg?
Of 1, sir.
Yeah.
0.0336.
And what's the volume for one? And we want it in kg per meter cube, so it had to be in SI units.
Sir, 4.2 times 10 to the negative 6.
Good, because we want the volume in meter cube.
Yes, sir.
Alright, so plug that into your calculator and let me know what you're getting. Yeah, true.
Sir, 8,000.
Shiloh, how about you? What you get?
8,000. So,
Okay, nice. Let me verify that. 0.0336, 4.2, 8. Nice, nice, nice. And the units?
eight-
8,000, right? Where's the units? How much of one?
Sir, kg/meter cube.
Right, kg slash meter cube. Or, again, you can say kg m to the power minus 3. That's fine.
Yes.
So let me tackle. We have these questions to do. Right? Calculate the relative density of steel, assuming that the density of water is that. So, Sheila, do you know about relative density?
No, sir.
Nah.
No,
So,
sir.
okay. When you hear the word relative, chances are you're doing what? Relative.
Average.
Nah. Like, okay, let me get an example. Imagine you do a math exam and your mom was like, well, you do alright, but not like as good compared to your sister. Like relatively speaking, you didn't do as good as compared to your sister. You know, so like relative, I don't mean that, but relative means you're comparing things. Relative, like how does one relate in terms of the other one? That's what it means. So the way to compare the density of steel to that of what?
Human density of water.
Right. So it's a really simple formula. Very, very simple. So relative density right, is just going to be the density of the substance within, right, density of substance all over the density of water. So in other words, here water, Shiloh, all I want to know, how much more dense than water is a steel. That's all. That's all. And I think you could even look at it and figure it out. If I tell you the density of water is 1,000 and the density of steel is 8,000, how much more dense is the steel than the water, relatively speaking?
7,000 kg.
Nah, 8 times. That's what I was looking for. 8 times.
Oh, yeah.
Yeah.
Uh,
So the density of the substance, which is the steel, it was 8,000. And this is the density of water.
1,000 kg.
Now, anytime you do it, anytime you're calculating something that's relative, there'll be no units. So this is just
Right.
going to work out to be 8. Yeah, so Shiloh, Javon, and Adel, if I say relative, I want you to compare two things. So, Shiloh, if I say calculate the relative density of steel to water, I want to know how much times more dense is the steel than the water. That's all.
All right. Yes, sir.
Yes, sir.
So, like, if steel is 8,000 and water is 1,000, then it's 8 times more dense than water. That's literally all it is. And there's no units.
Yes.
Let me do this fast. Alright, if I want to measure the diameter of wire, what will we use?
Oh. Scale.
Tell me, guys.
Micrometer. Oh,
Well, there was never really specific. Like I don't know how thin the wire is, but um, generally speaking, like since it wasn't very specific, we could use either a vernier caliper or micrometer screw gauge. But I would use the screw gauge. Right? We want to measure the mass of our coin.
e- electronic balance. Okay.
Electronic balance. What's the proper name for it?
Mm,
The triple beam balance.
Say that again.
Triple beam balance.
Yeah, triple beam balance.
ah,
And temperature, boiling water.
thermometer. Oh,
What kind? Well, here we didn't reach that part of physics yet, so you wouldn't really know. So I just put thermometer for now.
um,
But there are three main types: a clinical, laboratory, and there's the what's the other one again? What the multimeter? Uh what's the other one again? Types.
mercury.
None. That is classified under. No, I'm not talking about that one. I'm talking about the thermocouple. Thermocouple, yes, the thermocouple. Yeah, I don't think I'll even know about the thermocouple. It uses two different types of metals and join it. They put it at a junction, and basically the two different types of metals would react differently to the change in temperature, and it would produce a voltage at the junction, and you could calibrate that to read off at certain temperatures. Then we have electric current flowing in a circuit. What would we use to measure electric current?
The ammeter.
The ammeter.
Like,
And period of a pendulum. Period. What do we use to measure time? Time.
stopwatch.
Stopwatch, right? Alright, last question for the day. Two students are measuring the acceleration due to gravity g using a simple pendulum. Student A measures the value as 8.9 meters per second squared, and student B measures the value as 5 meters per second squared. Which one is more inaccurate? A or B? Who's
B.
Javon, who's more inaccurate? Alright, Javon, tell me if you're hearing me. Adil and Javon. Who's more inaccurate? What gravity supposed to be? Adil, what's gravity supposed to be? Can I hear Adil? Javon, what is gravity supposed to be?
I'm not sure.
9.81. Around 9.81 to 10. That's something we just calculated actually. Remember in the last question we find for G, you get 9.85, and then we calculated over here, and we had got 9.7. So like 9.81 to 10. Right. So anyways, state two possible errors in student B's experiment. What are some errors they could make? So you're dealing with a stopwatch.
Timing.
Say that again.
Maybe with timing. Installation.
Yeah, human reaction time.
Yeah.
Right. So it could definitely be reaction time. right? 2. You know what they could I use? I have a question,
Hmm.
right? If they use a stretchy string, what do you think will happen? You think the experiment would behave how it should, or like you go introduce
Yep.
another variable?
Mhm. Well, the length would change.
Yeah,
Well,
like think about it, Shiloh, and it doesn't length affect the period?
yep.
So if you use Javon, length affects period. So Javon, if you use a stretchy string, like something elastic, would the length remain the same
Yes, sir.
everywhere, or would the length change at different points?
Zero change at different point.
Yeah, so a possible error they could have probably use a stretchy string. You could probably say elastic string, but they're not supposed to do that. Maybe the person bad at maths, maybe they need to come to math vibes. So maybe they calculate the acceleration wrong, they use the wrong formula. So probably calculation errors, right? But I would pick one or two. And B, it is known that the exact value of G is 9.81. Suggest how student A can improve the accuracy of his experiment. What is the easiest advice you could give when you're doing a simple pendulum experiment?
There are like a larger number of oscillations.
I wouldn't say larger number of oscillations. I would say I feel like larger is not the.
Is
Yeah.
I feel
there
like
more?
right time more oscillations. Probably say probably like time time a. Let me make this sound nice. See, I want to like make it sound scientific and nice. So you could probably you could probably just say time more oscillations. That don't know that's the easiest thing you could do. Time more oscillations. That's literally all I could think about. Probably time more oscillations. If a elastic string is something that could cause error, what do you feel they should do? They could probably use a what? They could probably get a. Do you want an elastic string or a non-elastic string?
Non-elastic.
Exactly. Right. So probably use a inextensible string, meaning it has a really high tensile strength. And a good example of this would probably be nylon. Oh, you know what's nylon?
Yes.
Or like fission. Like what is used for fission?
Yes, sir.
Yes,
Yeah,
sir.
I think that's nylon. There's used for fission, but that's it. So I will send these notes, but see you guys in the next session. In the next session, I want to move on to vectors. I presume you guys will have done vectors already.
Yes, sir.
Scalars and vectors, we will look at that. But anyways,
Yes,
guys,
sir.
probably have a great day today. Take care. Later.
Yes, sir.
Same to you, sir.